Welcome back. In this video we're going to learn how a computer represents not only numbers but letters as well, using a system called ASCII and a more modern system called Unicode. If you haven't watched my video on binary, you might want to check it out before you finish this one so that we're all on the same page. I'll put a link to it in the description. In the last video we discussed binary and how a computer can store small amounts of electricity in transistors, which will either represent a 0 or a 1. And by chaining 8 of these bits together, we form a byte. And with 1 byte, what's the largest number that we can represent? Well, with 8 bits, if we switch all the bits to 1, you can represent a number as high as 255. And including 0, this will give us 256 possible combinations. If we wanted to count higher than 255, we would just need more bits. So that's great. With enough bits, it would seem a computer could count as high as we wanted to. Granted, we had enough memory. And to help drive this home, with 32 bits or 4 bytes, which is generally how a computer would store an integer or a whole number, a computer could count as high as around 4.2 billion. And our computers have millions, billions of bytes to work with. Now this doesn't account for negative numbers and decimal numbers, and we'll come back to that in a later lesson. But we know that our computers and our phones can represent more than just numbers. Most of us send text messages or emails that have English letters in them. So how do you think a computer would represent letters? If at the end of the day, all we really have are these transistors that can either represent a 0 or a 1. Well, you might reasonably think that we just need a mapping of a certain pattern of 1s and 0s to represent each letter of the alphabet. And so we could just all agree that A would equal 0, for example, and B would equal 1, and so on and so forth. But with this, we kind of ran ourselves into a corner, because if we're using numbers to represent letters like 0, then how do we represent the number 0? Well, there's a fix for this, and we'll see the solution in just a minute. But in reality, this is all that's really going on. We're just mapping patterns of 0s and 1s to different letters. And it's not quite as simple as 0 equals A, 1 equals B, but the decimal equivalent of the capital letter A is actually 65. And just so you can see it in binary, it's actually this pattern of 0s and 1s under the hood. The capital letter B is 66, C is 77, and so on. And humans have standardized this mapping of numbers and letters in the form of a system called ASCII, the American Standard Code for Information Interchange, which is just a fancy way of saying that a bunch of Americans got together in a room one day and decided that if our computers want to represent letters, that we should all use this standardized mapping. And if you look close, you can see capital A is 65, B is 66, and here's kind of that solution that we saw to a problem a second ago, where we gave up some numbers to represent letters. And it would just seem that we could represent numbers using other numbers. And this is where it gets a little mind-bending, like, would the computer use this pattern of all 0s to represent this null, or whatever this is? Or would it use the decimal equivalent 48 to represent 0? And this really is context dependent, and you'll soon see that it's ultimately up to the programmer to decide how the data should be interpreted depending on the program at hand. Inside your computer there's just a bunch of these patterns of 0s and 1s, and generally speaking, when you open up a text message, it's just 0s and 1s, but if it's a text message, the whole point is to send text, then the program should interpret those patterns of 0s and 1s as text. On the other hand, if we had the same pattern of 0s and 1s in a program like Excel or a calculator program, they should probably be interpreted as decimal numbers. Now, we're not going to dwell on these lower level binary details, but it's important to understand that at the end of the day, this is all that's really going on underneath the hood to represent letters in our computers using transistors and electricity. Now, chances are, if you speak a different language, then you might think, how could we represent characters from different languages, such as Asian characters or accented characters, and other characters we don't see here. Well, we just extend this system. ASCII is kind of an older system, which used 7 bits, but in reality it used 1 full byte to represent letters, meaning that we would have a total of 256 possible combinations that we could map to different letters, and technically ASCII only used 7 of the available 8 bits, so there was 127 combinations or mappings with ASCII. And this is fine for English and some symbols, but there are so many spoken languages in the world that we couldn't possibly represent all languages with only 256 characters, or let alone 127. The solution to this is just to throw hardware at the problem, and thankfully engineers have developed a system called Unicode. Unicode is a system that extends ASCII and uses not 1 byte or 8 bits to represent characters, but it rather uses 4 bytes or 32 bits. And with 32 bits, again, we have more than 4.2 billion combinations, which is plenty of characters to represent all spoken language, as well as some room for more playful things like emojis that we've all come to love, which underneath the hood are just characters. So to summarize and see this from a higher level, it would seem that by using transistors and storing small amounts of electricity, our computers now have the ability to represent numbers, letters, and symbols. So I want to give you a couple examples, or a couple exercises to try, of converting patterns of binary numbers into the ASCII equivalent. So let's start with this pattern of zeros and ones. Pause the video, try to work it out on your own. So the way we would solve this is to first convert each byte into the decimal equivalent. In this example, if we did out the math, we would get 72 and 73. Now if we just look at our ASCII chart, we can see that the representation of 72 is capital H and 73 is capital I. So the binary pattern of 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1 represents the word hi in all caps. Okay, let's do one more. Suppose we have this pattern of zeros and ones. How would we decode this into characters? Pause the video and try to work this one out. And again, the easiest way to do this is to first convert the binary numbers to decimal numbers, and then we'll use the mapping on the chart. So first we convert the binary numbers to decimal, and we see that we have 66, 89, 69, and 33. And then we just look at our chart. We see that we have B is 66, Y is 89, E is 69, and 33 is this exclamation mark. And so this pattern of binary digits that we have represents the word bye in all caps with an exclamation point. So thank you all so much for watching. I hope you got some value out of this video, and in the next one we're going to take a deeper look at how computers would use these same concepts to represent not only numbers and letters, but colors and images and videos as well.